Here we were discussing about the Picard's iterations. When these successive approximations are popularly known as Picard iterations. So when, under what condition that Picard iterations would converge. So we noted that when you take, let me write again. So when we took a rectangle which contains the points t, x, where t minus t naught is less than or equals to a, and mod x minus x naught less than or equals to b. So this is a rectangle. So we assume that f is f dx is Lipschitz, okay, on R. Then so you can write if 1, 2. Then the initial value problem x prime equals to f dx with x at t naught, which is equals to x naught, has unique solution. In the interval, okay, in the interval mod t minus t naught less than or equals to h. Okay, so where h is the minimum of a comma b by m. What is m? Where m is the maximum of mod f over R over this rectangle. Okay. So we proved this theorem, and as a remark, I said that if b is infinity, okay, if b is infinity, okay, so if b is infinity, that means that the f is Lipschitz globally. Okay, that means in that case f is Lipschitz globally. Globally means for all x in R, it is Lipschitz. So in this case, when b equals to infinity, you see this in this case, I can take this b to be anything. Okay, b to be anything. Therefore, h becomes automatically a. H becomes automatically a. What is this a? A is this, the entire interval that we have taken. Okay, entire interval of this R, where we have taken this rectangle. So this is known as the global existence theorem. Okay, so that is if f is Lipschitz globally, that is, so you may write this as a corollary. If you have a function f which is say, let me say it is from an interval a comma c, okay, cross the t belongs to this interval R to R is Lipschitz. Not locally Lipschitz. Lipschitz means that it is Lipschitz in the entire domain. Okay, it is Lipschitz in the entire domain AC cross R. Then the initial value problem, say x prime equals to f dx, x at t naught equals to x naught, has unique solution it has a unique solution in the entire interval a to c. So that is the global existence theorem. So this is also known as the global existence. The global existence is that wherever we are taking the problem, so if we are taking t variable, we are taking in the interval a to c. So if you take t to be in the entire R, then you have the entire R. So if AC is the entire R, okay, then solution exists everywhere. Exists in the whole real line R. Okay, so this is the case. So this is a very strong theorem because it's not that we see that many equations will have the solution in the whole of R. Okay, so for example, you take y prime equals to y square, a very simple equation. So this itself doesn't have the solution in the whole of R. Y at 0 is 1. Okay, so if you see that this solution is going to be 1 plus x square, that is 1 by 1 minus x. So that is y equals to minus 1 by 1 minus x. So this is the solution exists minus 1 by 1 minus t. So the solution exists only when mod t is less than 1. Okay, not always. So that is why this satisfying the hypothesis, the global Lipschitz, okay, which is not true here. Y square is not a global Lipschitz condition. Okay, so how did we prove this theorem? The theorem we proved is that we define the successive approximations, and then we use the Lipschitz continuity to show that these successive approximations actually converge. So now this raises a few mathematical questions. We proved a theorem which says that the following conditions are sufficient to get the existence and uniqueness of solutions. So this raises a couple of questions. What could be the questions? One, how we prove the theorem? We prove the theorem by showing the convergence of Picard iterations. Okay, so that's a very important thing. What is important is uniform convergence of Picard iterations. Okay, so is Lipschitz continuity necessary? That is, suppose if Lipschitz continuity is fails, okay, is this must for convergence of Picard iterations? This is one. Second, if it is, of course, a part of this question is that in this case, does the solution exist and it is unique? Okay, that is, can the solution be unique? Can the solution be unique? That is, suppose you have an initial value problem where the Lipschitz continuity is not true. Then what happens to the Picard iterations? And moreover, what happens to the uniqueness? Okay, so that is Lipschitz continuity must for uniqueness? Okay, and third question is, it's also in the same lines that first I'm asking whether the Picard iterations converge or not, and is Lipschitz continuity? Is this Lipschitz continuity a necessary condition? We see that this is a sufficient condition. Is this a necessary condition for generally for existence and uniqueness? Existence and uniqueness. Is this clear? So what we are asking the question is that suppose if I don't have, because I can write the successive approximations even without having the Lipschitz continuity. There is no problem for writing the successive approximations because if you know x0, you can define x1. If you know x1, you can define x2. and so on. So the successive approximations can be defined even if f is not ellipsis continuous function. Okay, so if we define like that, do those successive approximations converge? And what happens to the uniqueness? Can it happen that there is a unique solution even without successive approximations converge? Even without successive approximations converge? Okay. Because all the things that we have shown is through successive approximations. Right? So the role of successive approximations and ellipsis continuity, this is what we are questioning in existence as well as the uniqueness. And the second question is, by any other means, even if not Picard iterations, okay, by any other means, can we say that the solution is unique, even if the function is not ellipsis continuous? That is the second question. Okay, and third question is the ellipsis continuity necessary condition for existence and uniqueness? So everything is about the ellipsis continuity. How important is this as a necessary condition? Okay, sufficient condition we have seen. Is this clear?
Yes, sir.
Okay, so let us look at the first question. So what is the first question? Is about the Picard iterations. So there is an example given by Muller, the very famous mathematician, in 1927. It is a research paper which appeared in a very famous journal which called Math Z Script. Okay, so it is called Math Z. He gave an example. What does that example say? Take the function f dx. This is also a very important example to sometimes our idea of ellipsis continuity, we are misled sometimes. Okay, so this gives us what are the things and how careful we should be in checking the ellipsis continuity. So this is when t is less than r, take it to be 2t when t greater than r and x less than 0, and 2t minus 4x by t when t greater than 0 and x less than or equals to t square minus 2t t greater than 0, x greater than t square. So first thing is that this function is not ellipsis function. So f is not ellipsis. Of course, everything we are looking at around 0. So we aim to look at the problem with x prime equals to f dx with x at 0 equals to 0. So f is not ellipsis around the point 0, 0. How this is seen is this is look at f t comma 0 minus f t comma t square. If I compute this, right, so when x is going to be 0, when x is 0, you can see that it comes from here as 2t, third piece, minus f t comma t square, put x equals to t square in the same point, you get minus 2t. So this is 4t. So we write for the ellipsis continuity ftx minus fty upon x minus y. So right, so the here divided by t square. So we get f t0 minus ft comma t square on t square is 4 by t, which goes to infinity as t goes to 0. So that shows that no constant or ellipsis constant. Okay, no ellipsis constant. There is no ellipsis constant. Therefore, this is not ellipsis function. Now let us look at the successive approximations. Right. So let me write it here itself. I need the function. Okay, so x at 0 is 0, so x naught is 0, right? So x naught is 0. So come with x1t. x1t initial condition is 0, so it is going to be 0 plus f s comma 0, which becomes of 2s. So this is t square. Now come to the x2t. Okay. So this is f s comma x1, right? x1 is this, so s comma s square ds. So what is f of s comma s square? It is again minus 2t. This is minus t square. Now come to the x3. So this is f s minus s square. So right. So when x is less than 0, it is simply 2t. So this is when x is less than 0, it is 2t. So this is 2s, which is again t square. So what we are seeing here is for all x 2n plus 1 is going to be t square, and x2n is minus t square. So one is t square and the other one is minus t square. Okay, so these iterations doesn't converge, but you may say that okay, it has a subsequence which converges, right? So subsequences x2n plus 1 is t square and x2n is minus t square. But you see that this t square, okay, and minus t square, it's the limit, right? Subsequences converge to t square and minus t square. But none of these, either t square or t square, is not a solution for this equation. See that x prime, if I write for t square, right, x prime is going to be, for t square, it is going to be 2t. Okay, and f of t comma t square, f of t comma t square is going to be minus 2t. See, when x equals t square, if I put, I get minus 2t. So for if you take xt, if we take xt equals to t square, then we get x prime t equals to 2t. But f of t square is minus 2t. Therefore, x prime is not equals to f of tx. So it's not a solution. Similarly, for xt equals to minus t square. So you don't have, you have a situation here where none of the subsequences converge to the solution. Okay, it has subsequences which converge, but these subsequences doesn't converge to the solution. Okay, so the Picard iterations, you need not, when you are looking at only the limit, you don't have to look at the convergence of the sequence. even if you may say that even if it's one of its subsequents converge, okay, and if that gives me a solution, I'm fine, because ultimately I need a solution for this equation. So what's happening here is that none of its subsequences converge to a solution. Okay, so that is happening because this function is not ellipsis function. Now the next question is that, does this problem has a unique solution? Does this problem has a unique solution?
Hello sir.
Yeah. Yeah.
बट सर हम बाई एग्जाम्पल तो नहीं कह सकते ना कि ये इसके पास ये अगर लिखित नहीं है तो फिर हमारा ये कन्वर्ज नहीं करेगा. मे बी कोई दूसरा एग्जाम्पल गिफ्ट कर जाए.
दूसरा एग्जाम्पल में
बाई एग्जाम्पल तो नहीं कह सकते ना कि अगर लिखित नहीं है तो कन्वर्जेंस जो है फेल कर जाएगी या नहीं फेल करेगी.
Yes. So I need only an example.
दूसरा.
No, I am making a statement that ellipsis continuity, right? If you have ellipsis continuity must for looking at the convergence of the Picard iterations. That's what I am saying, that if you don't have the ellipsis continuity, Picard iterations need not converge. So I need to give only one example. In other examples, maybe it may converge. I'm not classifying those examples. I'm only saying, if you don't have ellipsis continuity, Picard iterations does not converge or need not converge. Let me say that way, right? So if f is not ellipsis, then Picard iterations need not converge. Need not converge to a solution. That's what our importance, right? It's here you see that Picard iterations has subsequences which converge to different limits. They have limit points, but it doesn't converge to a solution. Okay. If you don't have ellipsis continuity, the Picard, so that shows that the method of Picard iterations, okay, very strongly requires ellipsis continuity. Very strongly requires ellipsis continuity. So fine, that is gone. It doesn't have Picard iterations, is not giving a solution. Now can we say that this problem has a unique solution? Now,
no sir, there is a no unique solution, because t and t square both are going to be solution.
What? I didn't get once again.
T and t square both are going to be solution, so that are
they're not solutions, no? They're not solutions. That's what we saw.
Yes sir.
This is not a solution. T square is not a solution and t is not. But remember, this t and t square you are getting as limits of the limit points of the Picard iterations.
Yes.
Right? But there could be a solution otherwise. There could be a solution otherwise. We don't know. Only uniqueness means what? Uniqueness means if there is a solution, that is going to be unique. This is what the meaning of uniqueness.
Yes sir, हम भी ये कह रहे थे कि यूनिक सॉल्यूशन नहीं है, सॉल्यूशन है बट यूनिक नहीं है.
Why unique solution नहीं है?
क्योंकि
solution नहीं है. See, solution नहीं है is a different statement from unique solution नहीं है. Okay, solution is not there and uniqueness is not there. These are two different statements. That means that I am saying that this problem has a unique, it can have at most one solution. That is the meaning of uniqueness. It can have at most one solution. That's the uniqueness. Okay. It can have at most one solution is the uniqueness.
So sir, can we consider t square as a solution?
No. That's what we showed. T square is not a solution. So minus t square is also not a solution.
Yes sir. So मतलब इस function का तो solution ही नहीं है.
We don't know. Maybe there is another method where you get a solution for this. How will I know?
Yeah. Okay.
Picard method successive approximations method is not giving a solution. But that does not mean that the problem does not have any other solution. It may have any other solution. That is why we need to understand the theory, right? You may have different methods. Different methods are giving different solutions. Once if you know that the solution is unique, then all the methods are going to give the same solution. So you take, for example, y prime equals to y square. So I take y prime equals to y square. You can write the solution by separation of variables. You can write the solution by Taylor series, right? Are we going to get two different solutions? It's a natural question which people will ask, right? Am I separation of variable solution is different from the Taylor series? No, because the solution, now we know that this problem y square is locally elliptic, therefore the solution is unique. So any method that you apply has to give only one solution for this problem. Okay, so y square is fy equals to y square is local elliptic. So take y0 equals to 1 is local elliptic. Therefore, solution is unique. Therefore, if at all there is a solution, there is unique solution for this. So all the separation of variables method or Taylor series method or any other method, right, it's in the form of exact equations or anything, that has to give you only the same solution that you find by any method. All solutions are the same. That's why the importance of the uniqueness. Uniqueness means the problem can have at most one solution. Means problem, uniqueness means what? What is the meaning of uniqueness? Uniqueness means problem has at most one solution. At most one solution. I don't know if there is a solution. It may not have a solution. But it has, if at all there is a solution, it is only one solution. At most one solution. That means it is none or one. That's all. Okay. But if you show the existence also for the solution, there can be many ways to show the existence. I will introduce you to more abstract setting than the elliptic. Then you will see that this is where you will see the why the abstractness helps. Abstract mathematics helps, right? So that's why I'm emphasizing here that ellipsis continuity and Picard iterations gives one method of existence. But this is not all methods of existence. There are soon we are going to see different methods of existence where the ellipsis continuity fails. Where ellipsis continuity fails, but still you can show that the problem has a solution. Okay, so this is that we can show by using some abstract mathematics. So I will, when it comes, I will show you. Okay, so do the solution, so how do we see this? All the methods I am telling you to see how do we look at the uniqueness of the solutions. Suppose I take the problem x prime equals to f dx. So this part I have not yet included in the notes. I will include this and then send you once again at the end of my final lecture. So x at 0 is 0. Okay. Assume that f is a decreasing function. Is decreasing in x. Decreasing in x, I understand you know what it means by decreasing in x. Fix a variable t and the function is going to be a decreasing function. Okay, so if you look at this function, you can show that this f is a decreasing function in x. Right, so if this is a decreasing function in x, so let me write this as a theorem. Then solution is unique. That means then there exists, then there is at most one solution. At most one solution. So how do we show this? This all uses the simple basic mathematics, basic calculus. Suppose there are two solutions. Say phi t and psi t are two solutions. Right, so these are two solutions, means that both of them satisfies the equation, right? Phi prime equals to f of t phi, with phi at 0 is 0, and the same thing is true for psi also. Okay. And these are two different solutions and satisfying the same initial condition. See that at 0 both of them are 0, and there are, this is one solution and the other one may be this. Okay. Other one may be this. So let us look at the point theta. Okay. So let theta be such that phi at theta is less than psi at theta. This is maybe the point where they are okay, different. Then I consider the set S where t belongs to 0 to theta. Okay, at theta they are different, so you take phi t equals to psi t. So the set of points where they are equal. So it may not be exactly like this. So for some values they may be same, something like this. So it is this one, so this one, and the other one may be like this. Okay, so then you have this to be your theta, first element where they are, right? So the supremum of and let sigma be the supremum of S. Then phi sigma equals to psi at sigma because of continuity. Okay, because of continuity. And this S is non-empty. This is non-empty because 0 belongs to that. At 0, both of them are same. Okay, so at phi at sigma is going to be psi at sigma. So this is my sigma. Right, and say this is my theta. Now you look at the interval sigma to theta. Okay, look at the interval sigma to theta. In the interval sigma theta, you have the phi t is strictly less than psi t. Phi t is strictly less than psi t, and phi at sigma equals to psi at sigma. Now you look at the difference of these two functions. So phi minus psi at all these points, right? Phi minus psi at 0, it is at sigma, it is going to be 0, right? It is sigma, it is going to be 0, and all at all other points, say phi minus psi at theta is going to be negative. What do we have? Phi minus psi at sigma is 0, and phi minus psi theta is negative. Okay, so you have the sigma where it is 0, and there is a theta where it is negative, this function difference. Now you apply the mean value theorem for this. What does the mean value theorem says? Between these 2 points. So if I call this as another function, maybe z. Okay, so z at sigma minus z at theta is going to be, so if I call this as z, you have the by mean value theorem. Right, z at theta minus z at sigma. Have z at theta minus z at sigma is going to be z prime at a point t1 into theta minus c. Okay. Now you look at what is z at sigma. This is 0. Therefore, this is z at theta is equals to z prime at t1 times theta minus c. I can also write theta minus sigma here and remove it. So now you see that this is equals to z prime at t1 for some t1. Right? Z prime at t1 at some t1. But what is this z at theta? Z at theta is negative and theta minus sigma is positive. So this implies z prime at t1 is negative for some t1. What is z prime? That is phi prime at t1 is less than phi prime at psi prime at t1.
सर ये जेड थीटा माइनस जेड सिग्मा इक्वल टू जेड थीटा कैसे होगा?
Okay, by mean value theorem. Mean value theorem of differential calculus. Fx minus
sir,
Fy equals to prime at z into x minus y.
Yes sir. सर जेड थीटा माइनस जेड सिग्मा इक्वल्स टू जेड थीटा हो गया ना सेकंड लाइन में इससे.
Yeah, z prime at t1. Right? Z at sigma is 0, right?
Yes sir.
This is 0. This is
Yes,
0.
sir.
Therefore, z at theta by theta minus sigma is z prime at t1. So we have this relation. Phi prime at t1 is less than xi prime at t1. Okay. T1 is a point here. This is my point. Okay. So the other one you have between this sigma and theta, you have phi minus psi. Strictly less than 0. So something like this. So this is how your z looks like. Means, right? So phi at t is going to be strictly less than xi at t for t lies between this sigma and theta. And you have the assumption that f is decreasing. Okay? F of t phi is greater than f of t psi, because phi is less than xi and f is a decreasing function. But if you see what is f of t phi, phi is a solution, xi is a solution, right? This implies p prime equals to f t phi, which is greater than f of t xi, which is xi prime. That means phi prime minus xi prime is greater than 0. This is true for all points in this t2 sigma, but you have a point here, t1, where it is negative, and here it says this is positive. So this is a contradiction. Okay, so this is a contradiction. Therefore, the problem cannot have two different solutions. Is it clear?
Sir, last line.
Otherwise,
Focus
I will
clear.
repeat.
Sir, clear.
Last line. Huh?
No, sir, clear.
Yes, sir. Please repeat last line.
Yes sir. Last time.
Last line. Up to here is clear? Up to this is it clear?
Yes sir.
Yes, sir.
Phi prime at t1 is less than xi prime at t1 for some t1, just the application of mean value theorem from these two statements. Now I am using this statement. The other statement, that is phi negative. Phi is less than xi t in t for t in sigma to theta. So when phi is less than xi, I know that f is a decreasing function. F is a decreasing function means that f of t phi is greater than f of t xi. And what is f of t phi? Phi is a solution. Therefore, phi prime equals to f of t phi. And I know that f of t phi, which is xi prime. That means phi prime minus xi prime is going to be strictly greater than 0 for all points in this sigma to theta, wherever you have this. But I have one point t1 here. I have one point t1 here where phi prime is having an opposite sign. Phi prime is less than psi prime. So that's a contradiction. So this is happening because we assume that there are two different solutions. Is this clear?
Yes, sir. It is
In the
there.
previous slide,
Hmm?
in the previous slide, we have assumed sigma as the supreme of the set. So how would you know that the supreme belongs to the set?
Supremo?
Belongs
It
to
is
the
bounded,
set.
no, between theta. It is theta is the upper bound, right? And phi and psi are the continuous functions. No? You know that supremum is less than theta, therefore the supremum exists. No, theta is a real number. Supremum of the set is there is one bound,
The
therefore
set.
there is a least upper bound. Least upper bound means that there is a sequence which converges to that.
That is
And phi and psi are these are basic analysis. I'm not repeating all those things. Right? Phi and psi are continuous functions, therefore this is true.
Sir, is sir,
Tell me.
sir previous
Yes.
page. Sir, previous page S equals to T belongs to then equals to क्या लिखे आप?
Phi t equals to psi t. This is non-empty. This means non-empty. This is non-empty.
Okay,
This
sir.
set is non-empty. I'm sorry,
Okay.
I said non-empty, but I wrote it is non-empty. Non-empty because 0 belongs to this set. Phi at 0 equals to psi at 0.
Yes, sir.
Okay. So look at a point theta where they are different, and then look at the supremum of this set, and look at the set sigma to theta. We have to show that sigma to theta, this set is there is no elements in this set. No, that's what we want. So you take sigma theta as an interval, and in this sigma theta, an interval, and in this sigma theta, what are the relations we have? We have these relations: phi t is less than psi t, and phi at sigma equals to psi at sigma. This is all we have. This is one function phi, and this is another function psi. In this interval, we have these relations. So from these relations, we are getting a contradiction. Look at phi minus psi, okay, and apply the mean value theorem on that. Then you get a point T1 between these two, where phi minus psi prime is less than 0. But that cannot happen because f is a decreasing function. That's all. That cannot happen because f is a decreasing function. Okay. Now, another question is what I said is ellipsis continuous function. Ellipsis continuity is necessary. Okay, is necessary for existence and uniqueness. Right. So it is again not. It is not necessary. Say, for example, I take the equation y prime equals to y into sine 1 by y at 0 is 0. You can show that this function is not ellipsis function. This function is not ellipsis function. So you can do it in the tutorial session, or if you have difficulty in showing this, you can ask me. So y sine 1 by y. So I write like this. So the function where this is when y not equals to 0, and it is 0 when y equals to 0. I understand you understand this calculus things, right? Even if I don't write this, and the limit of it is defined through the limit as y goes to 0. As y goes to 0, y sine 1 by y has a limit that is 0. Okay. Right. So this function is not Lipschitz. Okay. So this is not Lipschitz. Around 0. Around 0. But you see that y equals to 0 is a solution. Is a solution. but y equals to 0 is a solution, right? It is not a Lipschitz function, but 0 is there as a solution. So that means Lipschitz continuity is not required for existence, right? And we also saw in the previous example that the function is not Lipschitz, but you have the uniqueness. So similarly here the solution is unique. Now this is very easy example to say that the solution is unique, and 0 is the only solution. How do I say this? So look at y sine 1 by y. Okay. If you look at the zeros of this function, okay, y sine 1 by y. So what are the zeros of this function? All y equals to 1 by n pi. Y equals to 1 by n pi are zeros. So call this as f. Right? They are zeros because if I put y equals to 1 by n pi, it becomes n pi into sine n pi, which is 0. All sine n pi is 0. So how these lines look like? These lines, as n goes to infinity, they goes to 0, right? So you have something like this. So these lines, there are so many lines. Right? Suppose this problem has another solution. Right? So the solutions are like, these lines are like this. Huh? Suppose there is a non-zero solution. So a non-zero solution means that there is a point where this is going to be non-zero, right? So suppose there is a point where this is non-zero, right? So there is a point where it is non-zero, non-zero solution. Say, let me call that as y1 at a point t1, which is non-zero, say greater than 0, right? Or greater than 0, say. Look at the initial value problem. Initial value problem requires that y at 0 is 0. That means this has to define a curve like this. It has to define a curve. Then only it becomes a solution of the initial value problem, right? And this curve, right? So this y1 intersects infinitely many of these lines. So when infinitely many lines are intersected, let's see if it intersects this line, say at this point, it intersected, right? Say y at y1, say at a point, some point, at some point it intersected. So look at that point. Say, let me call this as t naught y naught, t naught y naught. It intersected at a point t naught y. At this point t naught y naught, I consider this again this problem. Okay, at t naught y naught, with y naught non-zero and t naught non-zero. At this point, you consider again the same problem, y sine on by y, with y at t naught equals to y naught. Okay, sine 1 by y, by sine 1 by y. Right? At this point, you consider this. Now you see that this is going to be a Lipschitz function around t naught y naught. Because around t naught y naught, this function is going to be, the partial derivative is going to be bounded. Partial derivative is not bounded, or you can show that this is not a Lipschitz function around 0 only. But any other point, if you avoid 0, you can always find a small rectangle around which it is a Lipschitz function. Therefore, this problem has a unique solution. This problem has unique solution. But you see what is the what is happening. So these are the lines, and you have this. So this is where we consider the problem. Say T naught Y naught. So at this point you have two. So this is already a solution. This one is already a solution at this point, passing through this point, and also this is another solution which is passing through this point. See, this straight line is also another solution which is passing through this point. Right? This straight line is also another solution which is passing through this point. Therefore, that's not possible because the ellipsis function is there, right? So y equals to 1 of the 1 pi for n naught pi for some n naught is a solution, and y1, which we considered, okay, is another solution. So this is a contradiction to Picard's theorem. Picard's theorem says that if it is ellipsis, then it has to be only one solution. And away from 0, and you cannot say that, okay, at this n naught I have, so if I avoid this n naught, there is a unique solution, because these lines are actually converging to 0. So you can't find a single point, whether it is above the x-axis or below the x-axis, where the function is non-zero. The function is non-zero. The solution is non-zero. That means the function, this problem has only zero solution. Has solution that is only the potential value problem has only zero solution. See, so this problem has a unique solution which is 0, but it doesn't satisfy the ellipsis continuity. And for here we used exactly the idea of the Picard's theorem only, but at a different point, with an observation that all these lines are solutions of the differential equation, but not the initial condition. See, y equals to 1 by n pi satisfies the differential equation, and these lines are actually converging to 0. So that is for all n, right? These lines are actually going to 0. So there is no point where there is no positive point which doesn't intersect these lines, one of these lines. So that's the key of this example. Is this clear?
Yes, sir.
Yes, sir.
Okay. Good. So not only this, we can even have some examples where you don't have the ellipsis continuity, but still you have the uniqueness. I gave one case where f is a decreasing function in the variable x. So another case is there where you take the function which is just continuous but not Lipschitz. Just continuous which is not Lipschitz. Then from that you can have the uniqueness. Okay, so you have, for example, you take the function x prime equals to fx, okay, where f is such that, so you take x at a point tau equals to xi, and assume that f is strictly positive in the whole of R. X is positive in the whole of R. Then you can have, so basically fx is positive in the whole of R means that x prime equals to fx means x is an increasing function. X is an increasing function if there is a solution. So such a problem has unique solution. This has unique solution. Unique solution means at most one solution.
Hello.
Okay.
Sir.
Yes.
Sir, x tau equal to what is that?
Xi, another, just a symbol.
Okay, sir.
Just a symbol. Okay, so it is just a symbol, xi, x at tau equals to xi. Yeah. Okay, so this I will do in the maybe in the next lecture. So if you have any questions, you can ask me quickly.
Sir, in